Hi everyone. In this video we're going to look at applications of linear equations, or in other words, word problems. This is loosely based on sections 7.1, 7.2, and 7.5 in Math in Our World. Okay, so all of these examples deal with linear equations. So one thing that you need to do when you're looking at a word problem, if you're asked to write some sort of an equation, is to decide what form of equation best fits the problem. So we've looked at a couple so far, and mostly we're going to focus on two, either y equals mx plus b, and then ax plus by equals c. Alright, so this is slope-intercept form, the first one, and then the second one is standard form. Okay, so you'll start to notice a lot of these problems fall into one of these two categories, and if you notice that for your given information you have some sort of a rate, okay, that's what slope is a rate of change. Okay, so a lot of times you'll have like time and population, or a car's driving miles per hour, so you'd have miles and time, or maybe it's earning a certain dollar amount per hour. Okay, so then your wage, your salary per hour would be some sort of a rate. And if you notice that you have that in the word problem, as well as some sort of a starting amount, okay, then that word problem might best be represented by an equation in that form. Standard form is kind of like two parts being added to make a whole. So a lot of times what you'll see are word problems, like a classic one is like pounds of cashews and peanuts combined to make a trail mix. And maybe you know something like that, cashews cost, let's see, what's a realistic price? Cashews cost like $8 a pound, and then peanuts, they're a little cheaper, maybe they're $5 a pound, and then maybe you have $25 to spend making some sort of a trail mix. Alright, so you have usually two components, okay, like cashews and peanuts, and then maybe like some costs associated with those. Alright, so as we go through these examples, see if you can identify what type of equation is needed for these situations. So here's example 1. This is from page 376 in Math in Our World. The standard fare for a taxi in one city is $5.50 plus 30 cents per mile. Write a linear equation that describes the cost of a cab ride in terms of the length of the ride in miles. Then use your equation to find the cost of a 6-mile ride, an 8.5-mile ride, and a 12-mile ride. Okay, so we'll focus on the first part up to here. Okay, the rest of it is using the equation, so first we need to have the equation. Now, a linear equation, it's going to be in two variables, so we need to figure out what the two things are that are unknown. And this is what we're told. Okay, write a linear equation that describes the cost of a cab ride in terms of the length of the ride in miles. Alright, so those are the two variables. And anytime you have this phrase in terms of, okay, then that means we want to describe the cost, or have like cost equals, and then instead of a number we're going to have some sort of an algebraic expression that has a variable to represent the number of miles in it. Okay, so if we saw like write y in terms of x, that would mean write y equals a whole bunch of stuff with an x in there. Okay, so that's what we're looking for. Alright, now which form of the equation is this? Alright, well, if you have the two variables on different sides, then maybe what we're aiming for is something in slope-intercept form, y equals mx plus b. Alright, so if that's the case, then we need to look through this problem and see if we have some sort of a rate, or if we have a starting value. Alright, so now let's focus on the numbers that are given. Okay, the standard fare for a taxi is $5.50 plus 30 cents per mile. Okay, well this is just a fixed amount, the $5.50, so that could be the B. all right? And then 30 cents per mile, that word per indicates a rate. Okay, this is like a fraction, so it's 30 cents per mile, right? Or this is like the rate in dollars per mile. Okay, so here we have it. All right, so the cost of a taxi is $5.50 plus 30 cents per mile. Okay, well, you would multiply the 30 cents times however many miles you have on this ride. Okay, so let's try some numbers in here. Let's see if this makes sense. All right, so if this was a 10-mile ride, all right, think about how we would find the cost. Right, well, it's 30 cents a mile, so we would do 30 cents per mile times 10 miles. All right, and then that would be $3. And then it's plus $5.50, so that's some sort of a fixed fee or a cost, okay, kind of like a base rate. Okay, and then we would add those two together and we'd get that the cost for a 10-mile ride is $8.50. Okay, well, this equation is just describing more generally what we just did in that one specific situation. It's 30 cents per mile times the number of miles, and then you add on whatever that fixed rate was. Okay, so once we have this equation, then let's use this to solve for the different things that are requested, and we'll just do one of these, okay, and then I think you'll see that the rest are fairly similar. Okay, use your equation to find the cost of a 6-mile ride. So in other words, we are told what m is, the number of miles, and what we want to do is calculate the cost. So I just need to substitute 6 in place of the variable that I've used for miles. Okay, so this would be $5.50 plus $1.80. Okay, and then that would be, let's see, $7.30. All right, so you probably could have done this without an equation. You know, it's simple enough arithmetic. You could probably just figure this out, maybe even in your head or with the use of a calculator. But the goal here is just to see how you could use a linear equation to describe this. And then, of course, we would use the same skill in situations where it's maybe not so easy to calculate this in your head, or if we wanted to go on to more complicated applications. All right, a second example. From 1985 through 1997, the number of movie theaters in the U.S. increased by about 750 per year. In 1993, there were about 26,000 theaters. Write a linear model for the number of theaters Y. Let t equals 0 represent 1985. Okay, another phrase that you might see is linear model, right? And basically you're being asked for an equation. We call it a model because it sort of describes the situation. It kind of approximates it, but it's not perfect. So, in other words, the number of movie theaters is increasing, and just for this period of time, 1985 through 1997, okay, so like if I made like a little timeline here, just for that period of time, then the number of movie theaters in the U.S., because it was increasing, it kind of looked like a line. Okay? But then it's no guarantee that, you know, what happens either before 1985 or after, you know, would look like a line at all. So that's why we call it a model. All right, so the other thing we need to work with here is the fact that we're given this t equals 0 to represent 1985. So sometimes if the numbers are rather large, then rather than substituting in 1985 into the equation to find the number of theaters, sometimes we just like smaller numbers. So we'll just let the value 0 represent that initial year. So it's kind of like the starting time, the initial time, or like time 0. All right, so then t equals 1 would represent 1986. Okay, t equals 2 would be 1987, and so forth. All right, so then think about, let's see, we know it's 85 through 97. So then what value of t would match 1997? Okay. Well, just think about how many years we've, what's the difference between 1997 and 1986? All right, and that's 11 years. So then it would be the same thing for the t's. So then t equals 12 corresponds with 1997. All right, so we need to write a linear model. So one thing we can do is decide if this is slope-intercept, y equals mx plus b, or standard form. And you may have had time to look at this and kind of pick out the fact that one of these numbers is a rate. We have this increase of theaters by about 750 per year. Okay, there's that word per again. So this is 750 theaters per year. Okay, so this is a rate that's describing theaters per year, which just happen to be our variables. The number of theaters is y, we're told that. Okay, and then we're letting t represent time in years. So we've got a rate of change between y and t, the theaters and the year. All right, so that's a rate, so that can be the slope. How about a starting amount? So notice in this one, our starting year, okay, is 1985. And remember that if we were looking for, if we're looking for this y-intercept, this b, okay, remember that that's actually the point 0b, okay, because that's a y-intercept. The x-coordinate is 0. But when t equals 0, that's 1985, and I don't know how many theaters there were in 1985. We're not given that information. So you have a couple options. Since we have this, we do have this piece of information. In 1993, there were 26,000 theaters. So one option is to just kind of back up 750 per year from 1993 to 1985. That's kind of the long way of doing it. Okay, and that would certainly work. Now here's a second option, just in case you had, a number that was really far off. So like, let's say we didn't know 1993. Maybe we knew the number of theaters in 2015 or something like that. Okay, much farther away from 1985. So here's what we'll do. We'll start out with what we know. Okay, so I'm going to fill in y equals mx plus b. I have y equals, and the slope, it's 750 theaters per year. And then we're just using a t instead of an x, but you can call it x if you like. And then I'm just going to write plus b for now, since I don't know what that is. Okay. Now I'm going to fill in the information that I do know. Right, I have a year, and I have a number of theaters. Okay, so in other words, this is like a word problem way of giving you a point of a year and the number of theaters. Okay, well, 1993, I need to know what value of t goes with that. All right, so remember, t equals 0 is 1985. So 1993 is 8 years later. So then t would be 8. Okay, and when t is 8, this is telling me that y, the number of theaters, is 26,000. Okay, so now what can I do with this information? Well, I can substitute those into this equation that I have. All right, so if I substitute 26,000 in for y and 8 in for t, now I can actually solve for b and figure out what the y-intercept is. Okay, so then 750 times 8 is 6,000. Okay, and then subtract 6,000 from both sides of the equation, and that gives me that b is 20,000. All right, Now you could have found the same thing if you started at 26,000 and if you subtracted 750 repeatedly, okay, kind of backing up from 1993 all the way back to 1985, then you should end up with the same thing with 2,000. All right, so then write a linear model. We can finish this one off now. For part A, I can substitute back in what I know the y-intercept is, 20,000. Okay, so that's part A. Part B, use the model to determine the number of theaters in 1997. So a lot of times if you're asked to use an equation, you're basically just given one value of a variable and asked to solve for the other one. All right, so here we have a year, 1997, and what does t equal in that year? I think we said t was 12. So we're asked to determine the number of theaters, or in other words, solve for y. So we simply want to substitute in 12 in place of t, and then just use order of operations to simplify this and get a value for y. Okay, so 750 times 12 is 9,000, plus 20 is 29,000. All right, so there were 29,000 theaters in 1997. All right, and then part C, in what year will there be approximately 30,000 theaters? So if we're using the equation, same thing. This time we have the number of theaters, we know y, and we're trying to solve and find t, find the year. Okay, so we have 30,000 equals 750t plus 20,000. Right, subtract 20,000, that's 10,000, equals 750t. And then divide by 750, and that gives that t equals 13.3 repeating. Okay, and then we just need to translate that to an appropriate answer for the question. So they're asking in what year. All right, so this is year since 1985. So if you add 13 to that, okay, that would be 1998. And then that 0.3 repeating, that just means it's somewhere in the middle of the year, a third of the way into the year. Okay, so it's in 1998, or you could say like in between 1998 and 1999. All right, here's a third example. Kim purchases a bonsai tree from a local greenhouse. Its height, h, in inches after t years can be modeled by the function h of t equals 1.5t plus 10. Find the slope and y-intercept and interpret them in the context of the problem. So here we actually have the equation, and it's given in function form. So let me just remind you about this notation, this h of t. Okay, this is like a label. This is in place of a y, so that we could have said like y equals 1.5t plus 10, but we're using function notation to emphasize the fact that the height depends on the time. Okay, so how tall the tree is depends on how many years after the time that it was purchased. So if we had something like h of 3, that would mean, h of 3 equals, that would mean the tree's height after 3 years is a certain value. All right, or another way of, or another question we could ask, if you're given h of t equals 7 and asked to find t, okay, then this is saying that the height of the tree after t years is 7 inches, and then we're supposed to find the number of years, okay, after which the tree is 7 inches tall. You may have also seen function notation with like f of x. Okay, so then the function of x is something else, and same thing, there's this whole piece could be replaced by a y. The other thing to remember is that this doesn't mean f times x, and in our example it doesn't mean h times t. Okay, it's just one big label that kind of all sticks together. Okay, so find the slope and y-intercept. Well, let's do that first. And we're actually given this in slope-intercept form. Okay, this is like y equals mx plus b with just different variables. So right away, you should be able to pick out this number in front of the t. Okay, that's the m, that's the slope. So the slope is 1.5. If you like it as a fraction, you could think of this as 3/2. Okay, and then find the y-intercept, that's this number at the end, okay, the plus b. So the y-intercept is 10. Okay. Now interpret them in the context of the problem. This means describe what slope and y-intercept mean in terms of the two variables. So what does this have to do with the tree's height in inches and t in years? Alright, so remember that slope is the change in y over the change in x. Okay, and that's your symbol for change, okay, or like a difference. So when we look at the slope, we're going to use the units of whatever y is divided by the units for whatever x is. All right, so here, instead of a y, we have this h of t, right, or we have height. And then instead of x, we have a t, and t stands for years. All right, so the slope is either 1.5 height over years or 3.5 height over years. Okay, and height is actually in inches, so maybe it makes more sense. I should probably write it like that. Okay, and then we could read this as inches per year. So basically, the slope is telling us how quickly this tree grows, and okay, I could even write a sentence to answer this question. So I could write the tree grows 1.5 inches per year. And that's what the information that we have from the slope. Okay. Now you could have also said that the tree grows 3 inches per 2 years, okay, if you like to think of this as 3/2. Okay, so what about the y-intercept? How do we interpret that? We're going to think of this as like a fixed value or a starting value. And remember that if we wrote this as a point, okay, this is not really just 10, it's actually 0, 10. So we have an x value, or in this case, t for time, and then we have an h of t value, or a height in inches. So this is like saying that the tree's height after 0 years is 10 inches. And it doesn't directly say this in the problem, but if we think of 0 years as maybe when she purchased the tree from the greenhouse, then basically we could say that when she bought the tree, its height was 10 inches. Okay, so tree was 10 inches tall at time of purchase. Alright, so if you're asked to interpret in context, basically what we're looking for is just an answer that doesn't have any mathematical terminology in it. So no mention of slope or intercepts or y's or x's or anything like that. It's all in terms of the actual units and things mentioned in the problem. Alright, enough said about that one. One last example of a word problem with a single equation. Alright, Speedy Delivery provides a holiday flower delivery service. This year the company needs to earn enough revenue to pay for $2,300 in repair costs for their delivery vans. On average, it costs the company $3 to make each delivery. Speedy charges its customers $5.50 per delivery. Okay, so this is an example of a problem in which we can model some business terminology using linear application. All right, so we have cost and revenue, and in case you don't have a good working definition of these, let me give you one. All right, revenue is just the amount of money that the company is making. All right, so this isn't profit, but this is just like, you know, money, like incoming money, we could say. All right, so when they When a company sells products, then whatever the consumer is paying for those, all of that money coming in, that's going to be split up, and some of it goes to pay costs, but some of it goes towards profit. All right, so another way of saying this is that revenue would be just the difference between, or I guess we could say it this way, it's like the costs that the company needs to pay off, and then whatever's left over would be the profits. All right, and then here when we talk about costs, it's cost to the company, not to the consumer. All right, so this is an amount. This is not the amount that a person is paying for these flower deliveries. This is the what it costs the company to make the deliveries. So think about like the gas for the vehicles, making the deliveries, salaries for employees who are driving. All of that would go into the costs. Okay, so part A, we need to express the company's yearly costs as a function of X, the number of deliveries made. Okay, so cost is a function of X, so that means that cost equals some equation involving an X. Okay, where the cost depends on how many deliveries are made. All right, so all of these will follow a very similar pattern, and what we have is that cost, all right, the company's costs can be broken down into two parts. There's some sort of a fixed cost, and then there's some sort of a variable cost. So we have the variable cost is like the cost for each one of the things they're making, or the products they're selling, or in this case the deliveries they're making. Okay, so it's a variable cost times the variable, in this case X, okay, plus whatever fixed cost they may have. So fixed costs would be things like rent for the building that they're working out of, or the warehouse or something like that. Maybe like a utility bill if they just have a set amount that they pay for electricity each month, insurance, things like that. Variable costs, okay, would be like supplies to make different items, or in this case, whatever the costs are for each of those individual deliveries. So the more deliveries you make, the more variable costs you will have. Okay, so in this problem we have two types of costs. Okay, we've got this $2,300 for repair costs on a delivery van. Okay, that's a fixed cost because they have to pay that off regardless of how many deliveries they make. Okay, so that's added in there. And then this $3 cost per delivery, that's the variable cost. The more deliveries they make, the more $3 costs they will incur. Okay, so we have company's costs would be 3x, $3 per delivery, plus $2,300. And this is like a huge amount that they're going to need to pay off by making a bunch of these deliveries. All right, revenue. All right, revenue is also a function of the number of deliveries they make, and this is just the incoming money. So how much are they earning per delivery? Well, they're charging their customers $5.50 per delivery, so that's the amount they're making. Okay, so that's $5.50 per delivery times X, however many deliveries they make. Okay, so we've done A and B, and then in part C, how many deliveries does Speedy need to make in order to break even? So this is another business type phrase here, what it means to break even. All right. I guess you may have seen this in other contexts as well, but in this case, break even, we want to know when are they able to pay off the costs and start making profit. So what I want to do is figure out when revenue equals cost. Okay, and that's the break even point. And then after that, they'll start making more. Okay, so you may have seen, like if we looked at a startup business or something, they're initially going to have some pretty steep costs. All right, and maybe they're not, making as much at the beginning. Okay, so their revenue, maybe nothing's really coming in as they're getting started, but eventually at some point, hopefully the amount they're making will overtake the costs, and then once that happens, then they'll start making a lot of profit. All right, so algebraically we can figure this out by setting the revenue equal to the cost, right? Or setting this revenue equation equal to this cost equation. So we're going to do 550x equals 3x plus 2,300, and then solve for x. Okay, so I'll subtract 3x from both sides. I'm combining like terms here, so that's 250x equals 2,300. Okay, and then I need to divide both sides by 250 to get x by itself. Okay, so 2,300 divided by 2.5 is 920. So x equals 920. So in other words, when they make 920 deliveries, they should have the exact same annual costs as they do revenue. All right, so if they make 921 deliveries, then that's when they're going to start making a profit. All right, we'll stop there. So I just wanted to give you a variety of examples of what we can do, different problems we can solve with linear equations. All right, so we saw some examples where we needed to write the equations ourselves. Okay, we had one, this y equals mx plus b format. Okay, here's another one. We looked at already an equation that was given and interpreting the slope and y-intercept. Okay, and then this sort of a business type application looking at expressing cost and revenue with equations. All right, and using these to help calculate what's needed to start making a profit. All right, in the next video we will look at two applications involving a system of linear equations.